Today we want to talk a little bit more about integration by parts. You recall a couple days ago, we introduced integration by parts as the anti-product rule. And there was the formula. The formula is the integral of u dv is uv minus the integral of v du. Remember the steps were step 0, not substitution. Step 1, the givens. Step 2, find. Step 3, plug in. And step 4, evaluate the secondary integral. Some interesting things that we could do with integration by parts. We can integrate by differentiating. So yesterday, we figured out the integral of natural log was x ln x minus x plus c. And we found that by actually differentiating natural log in the u slot of integration by parts. So we differentiated natural log into a 1 over x. Then the secondary integral, there wasn't any natural log in it anymore. And so that changed how we approach the secondary integral. The same thing is true with tangent inverse and sine inverse. And what we want to notice is that the derivative of inverse tangent, or the derivative of arctangent, is 1 over 1 plus x squared. So we go from this inverse trig function to a rational function. That's the same thing that happened with natural log. We had natural log, well, it wasn't an inverse trig function. We have this natural log function, and the derivative is a rational function. And a similar thing happens with inverse sine. The derivative of inverse sine is 1 over the square root of 1 minus x squared. So we don't get a rational function, but we do get a radical function. And that's a big shift in what's being represented in our integrals. We go from an inverse trig function to an algebraic function. So that's one of the cool tricks of integration by parts. Then we noticed that some problems are going to require multiple applications of parts, multiple parts. And this is where we can differentiate u down to 0. So if one of the factors will differentiate down to 0, that might be the strategy for integration by parts. And then the other trick that we found was the original integral appears in the secondary. So yesterday we were integrating, and we were integrating x to the 5th natural log of x. And the way we integrated it, using our newfound knowledge of the integral of natural log of x, we had 5 copies of the integral of x to the 5th ln x show up in our secondary integral. So the strategy there is when our original integral appears in our secondary, we move it over. We move all those copies over to the other side. And then we just have to divide by a coefficient at the end. Any questions? All right. We're going to integrate a function. And this is going to be for parts purposes. We're going to be emphasizing the original integral appearing in the secondary. That's a parts process. So we're going to integrate this function. We're going to think about this function today, or this integral today. Cosine squared x. What we noticed first about cosine squared x is that I forgot to put the discussion where I was going to say which products of powers of trig functions are substitution problems when we try to integrate them. I was going to do that on Friday. I didn't do it on Friday. I said, well, I'll just do it on Monday because I don't work weekends. And then Monday happened. And at the end of the day on Monday, I was like, oh, there's something I forgot to do today. I wonder what it was. Oh, well, computer's off now. And then just now I got reminded. So we notice that we don't have any odd powers of cosine or sine. I can't save one thing to be the dw. I can't save one factor of cosine to be dw. because then I've only got one cosine. I've got cosine to the first because I'm saving one to be the dw. And we can only convert them in pairs if we're going to get away with integrating products of powers of trig functions with substitution. So here's one of our cases of products of powers of trig functions that is not substitution. It's just even powers of sine and cosine. So step 0, not substitution. Step 1, assign parts. Now, there's a lot of ways that we can do this. I've got 2 factors of cosine. Let's see, which one is the most wrong? We're going to do this wrong a couple of times first. So let's try it. Let's suppose that we said dv is just cosine squared. Well, that doesn't make any sense. If I knew that, I wouldn't be doing parts. I would just be writing down the integral of cosine squared. So this is not going to work. That is not how we're going to deploy our parts. Well, one of our strategies is to switch them around. Let's say u is cosine squared x. And that would make dv just 1 dx. So if one way doesn't work, you can just try switching the parts. All right, so that would be step 1. Write down our givens. Step 2, find du and v. So du, oops, and automatically, I'm just not liking this right now, because derivative of cosine squared x is 2 cosine x times minus sine x. We have to use the chain rule. So I'm going to have minus 2 cosine x sine x dx. And v is equal to x. So there are my 4 parts. So this is not the way we did it. That one did not work. Now we look at the integral that we're going to get here, and we have made things substantially worse. In particular, our secondary integral is not just going to be some combination of sine and cosine. I've also got this x mixed in as a factor. If this x had showed up as a term, we wouldn't have worried about it, but it showed up as a factor, and that messed everything up for this integral. Let's take a look at what happens when we write this down. So we end up with the integral of cosine squared x to x is uv. No big deal mixing as factors our algebraic and transcendental functions here, minus the integral of v times du. So it's minus 2, so I'm going to put a plus 2 on the outside. So I don't like where this has headed. I've got a mixture of x and cosines and sines. So this seems like things became worse. It doesn't mean we're going to abandon this completely, but we're going to say, is there something else that we can try? We don't like where this is because we've taken our original integral, which was just cosines, and now we not only have cosines and sines, but also x. If this x wasn't there, then we could just integrate this with substitution and everything would be cool. W could be cosine, dw is sine. W could be sine, dw is cosine. They're both odd powers. But this means we are not going to be doing substitution. We could do parts on this. But there's another way we could split up these integrals. We don't want to abandon this, but we don't like where this is headed. Does that make sense? It's not that we're saying that this is wrong. We just don't like where this is. So let's go backtrack a little bit and see if there's something better. I don't like this x mixed with the cosines and sines. So here we're going to bring us to, this brings us to the actual point of doing this cosine squared, even though this is not how in general we're going to be integrating even powers of cosines and sines. What we want to use this example for is to point out that this cosine squared represents two factors of cosine. And I just need to split up u and dv as factors. So I don't have to have the two cosines together all the time. They don't have to be the dv, because I can't. They don't have to be the u, because we don't like where it ended up. So we could try splitting the cosine. So here's another option for parts. One of our other strategies for integrating by parts is to split powers. So I had two factors of cosine, so I'll just keep one over in the dv and then one over in the u. So that's step one. Find your givens, or establish your givens. Step two, find the other two parts. Root of cosine is negative sine, and the integral of cosine is sine. Next step, put things together in the parts formula. So we're going to subtract the integral of sine times negative sine. So the negatives will cancel out. So I have negative sine, and it should be squared. Everybody still with me? Nothing up my sleeves. So now our secondary integral is sine squared. This should make us both suspicious, and you should definitely be suspicious, because I'm going to be like, oh, well, let's just do the same thing what we already did. I'm sure it'll work out just fine. It's not going to work. I'm going to try the same thing, splitting the sines and the cosines, or just, splitting the two sines over u and dv, and we're going to watch it not work. So we might look at this sine squared and say, I'm going to use the same strategy that I used on cosine, because I'm in the same situation. Now that's the important part right there. I'm in almost the same situation, so I'm going to use the same strategy. Do we think this is going to get us anywhere? No, because it never does. If you identify what a problem is and you apply it and attempt a solution that doesn't work or puts you back in the same situation, then that solution is not, don't just apply it again. But we're going to do that anyway, because we're going to pretend that we didn't notice that because we're new to integration by parts. Even though we've done like, what, almost 6 examples. I mean, you should be ready to turn pro at this point. I mean, 6 whole examples. You're ready to go, right? So let's try the same strategy and watch it not work. The u is sine x, and dv is sine x, dx. And then our find is du is cosine x dx, and v is minus cosine x. Initially, it makes sense. This is the thing that we did before. We should try it again, even though it didn't actually get us anywhere, but we might not have noticed that we didn't get anywhere. Integral of cosine squared, integral of sine squared. So what we have is that the integral of cosine squared, after our integral jump, we have cosine sine plus the integral uv minus the integral of v du. I shouldn't have put the plus because we're not plussing or minusing. Oh, I'm going to use parentheses. Okay. So now I'm going to put our second set of parts into the parts formula. I'm going to write uv minus the integral of v du. Mashed together into the parts formula. And now we can see that this has not gotten us anywhere at all. It makes sense because we were in the same situation. We did the same thing. We should expect the same result. Now we can try this again, but this is a case of the original integral showing up in our secondary. Notice that what happens here is that cosine x sine x minus cosine x sine x. So what this equation is telling us is that the integral of cosine squared dx is equal to the integral of cosine squared dx. Well, no shit. So this all leads to no conclusion. We get nothing new here. So that didn't get us anywhere. Obviously, it didn't get us anywhere because we applied the same solution when we were in the same situation. And so we're right back to where we started. We know nothing. But I'm sure if we keep pursuing this war on drugs, this time for sure, this time it'll work. Oh. That's my favorite example of humanity just not learning its friggin' lesson. Ban alcohol. Amendment to the friggin' Constitution. Banning alcohol. They're like all, yay! And then like crime and debt and the wrong people making money. Not that people weren't making money. The wrong people were making money. And so they said, you know what? Fix that. 21st Amendment. Repeal prohibition. I think it was 18 and 21. Anyway, there was one outlawing it and then one. Now we become aware of drugs artificially fueled by people that didn't like what these wrong people were doing. So we say these things are bad. We should ban them. And did anybody like look at the Constitution? It's like, oh, look what we went through doing that. An entire friggin' amendment to the damn Constitution that we had to undo with another amendment to the Constitution. I mean, we can talk about things taking an act of Congress as being difficult. Things that require an amendment to the Constitution is even worse because it requires multiple acts of Congress. So, multiple acts of multiple Congresses. Yeah, we're like, all ban the booze. Oh, we don't like that. Unban the booze. And it's like, oh, maybe we should ban drugs. Yeah, okay. That's what we're doing here. We're looking at the same problem, applying the same solution, and wondering why we didn't get anywhere. So I'm here to tell you this is why we didn't get anywhere. We were in the same situation, and we attempted to apply the same solution. When we applied that technique in the beginning, it got us to a place that was essentially the same. Everybody see where we're at? If you didn't make any forward progress last time, you're going to have to try something else. You're going to have to come at the problem from a different angle. So let's pick up where it went wrong here. This strategy was the same. It's not going to get us out of anything. So let's retcon back to this line because I'm still on this splitting the cosine. So splitting the signs didn't get us anywhere. Splitting the signs didn't get us anywhere. Splitting the signs didn't work. We need to do something else. As usual, the most important thing to attempt is something. Notice that we're looking for something else to do, and we're also looking at trig functions. If you're looking for something else to do, and you're looking at trig functions, the first drawer you open is the trig identities drawer. I go, well, you know what we haven't done yet is smack this with some identities. And that's exactly what we're going to do now. Because we're going to replace sine squared, since we know splitting the signs don't work. We're going to replace sine squared with 1 minus cosine squared. That gets us one of our variations at the top, where the original integral appears in the secondary. But this time, rather than just telling us that the integral of cosine squared is equal to the integral of cosine squared, we're actually going to get somewhere. We're going to replace sine squared with 1 minus cosine squared. So it looks like the integral of cosine squared x to x is cosine x sine x plus the integral of 1 minus cosine squared. Now we're in the category of the original integral appearing in the secondary. But the important difference is it is just one of the terms in the secondary. I'm going to split the 1 minus cosine squared into the integral of 1 dx minus the integral of cosine squared dx. So I'm going to rewrite this integral. Yes. All I'm doing is replacing this sine squared with 1 minus cosine squared. That is increasing the number of cosines, but it's increasing the number of cosines in a good way. So all I did was replace sine squared with 1 minus cosine squared. We can always do that if it's convenient for us to have two terms, or in this case, the convenience is we get to look at the integral of cosine squared. So after we split these terms, we'll have a copy of the original integral. After we split those terms, we will have an original integral in the secondary equation. And we're just going to add whatever copies of the original integral to both sides. We're going to gather like terms. So here we are having split that integral over its terms. Now we have the integral of 1 dx. That's easy. That's just going to give us an x. Then the other one, the other term, is the integral of cosine squared x dx. So what we're going to do is take this minus 1 integrals of cosine squared x dx, and we're going to add this to both sides. And so on the left, we'll have two copies of the integral of cosine squared. This is the strategy. That's the strategy when the original integral appears in the secondary. Then we have cosine x sine x. The integral of 1 dx is x. Then all we have to do is divide everything by 2. Oh, this shouldn't be a minus 1. That should be a plus 1. Any questions? So this was a lot of effort spent on integrating cosine squared, especially when this is not how I recommend you integrate cosine squared. Notice that we used an identity because we got to a place where we had trig functions and we hadn't started with identity. We hadn't looked at any identities yet. So if that's the case, we should go back and re-examine from the beginning. Are there any trig identities that would help us out here? Now, in this case, if I replace cosine squared with 1 minus sine squared, I have essentially the same problem. The integral of sine squared is just like the integral of cosine squared. So the actual way we should integrate even powers of cosine is to use the double angle identity. So all we have to do now is remember our double angle identities. Now, there are a lot of great mnemonic devices for remembering your trig identities. Here's my favorite one. Hey Siri, what are the double angle identities in trig? That's a little bit high level, isn't it? But this is my favorite mnemonic device for remembering my double angle identities, because there's lots of pluses and minuses going around, and that means the order of the terms. So I wonder if the first image is going to tell me what I need to know. Oh, lo and behold. Let's see. Oh, this is like in the middle. Dang it, Google. Here we go. Now, notice that the first thing is, if you get to use a cheat sheet on the test or something like that, teachers are always allowing like custom-made cheat sheets, right? So you only write down the things that you know you're going to forget. But I say that's not good enough, because a lot of times that's justified by saying, well, if I didn't know, I would look it up. So here's how cheat sheets work in my game. I make the cheat sheets, and some of the information on the cheat sheet is wrong. Some of the double angle identities are incorrect. Do you know the difference? Because if you're going to justify looking things up for using cheat sheets, first of all, just let students use Google during the test. If Google can defeat your test, maybe your test is not very good. You'll say, well, they'll just use Google and solve the test that way. It's like, well, maybe that means your test isn't very good. Why are you doing this activity if this is just stuff that we can Google? You know what I mean? No shade on teachers that actually do this. It's fine. But I just want people to recognize we only do it that way because we've always done it that way. And that's a terrible reason for doing things. So notice I did have to find not the first result, but one of the first 5 results. Tell me what I need to know. Sine of 2a is 2 sine a, sine of 2x. Sine of 2x is 2 sine x cosine x. But we have some other ones. The cosine of 2x is cosine squared minus sine squared. Now, because cosine squared and sine squared are related through squares, we have 2 other versions of this. I can write this as 2 cosine squared x minus 1, and also 1 minus 2 sine squared x. There's also a tangent one that we don't really need this time, but I mean, I have a trig class, so it's hard for me to not write down trig identities. Trig is one of those subjects that it's a really cool subject all on its own, but it's even better if you think about putting trigonometry in history. Think about the study of what we know about trigonometry and the history of knowing it. It makes it much more interesting. We just get the watered down results. We don't get to watch the original story unfold. It's like math class is nothing but spoilers, pretty much. That's all. So here's one that's going to be useful for us. A cosine of 2x is 2 cosine squared minus 1. Take a look at what these identities buy us. We take cosine squared, which is clearly a difficult thing to integrate. But if we can convert a cosine squared into a cosine of 2x, this is a trivial thing to integrate. Because the integral of cosine of 2x is just a half sine of 2x, right? I'd rather integrate cosine of 2x than cosine squared. This has been messy with parts. This is borderline trivial. So cosine squared is messy using parts, but integrating cosine of 2x is borderline trivial. So what if instead of, I'm going to rewrite this, we solve this identity for cosine squared x, we see that cosine squared x is 1/2 plus 1/2 cosine 2x. Just add 1 divided by 2. So I can trade my cosine squared for a 1/2 plus 1/2 cosine of 2x. From a calculating things on the calculator standpoint, that doesn't get me very far, but from an integration standpoint, this takes my messy integral to a pretty easy one. So we start with cosine squared x dx, and we magically remember our double angle identities, because everybody remembers these all the time, and they don't have to look them up. It's not like your teacher who's losing his mind, who has to look these up to make sure he puts things in the right order. That's actually so I make sure that I get this sign right, because if I don't look at it, I put a minus here, even though I know what the answer is supposed to be. It's crazy. Notice that this is still in the integral because all I did was rewrite cosine squared with in a different form. Now we've got terms, the integral of 1/2 and then the 1/2 cosine of 2x. I can break that up into terms. The integral of 1/2 is a 1/2 x. The integral of cosine of 2x is sine of 2x divided by 2. No parts required, barely a substitution. Now, at this point, you might be calling foul, because this does not look like what we had before. But I put a box around it, so the problem must be done. They must be the same. So let's move on. I'm just kidding. I'm not going to get away with that. Notice that this integral, function is a 1/4 sine of 2x. That's not what we had up above. We had cosine x sine x. So if we grab the double angle identity for sine of 2x, I can replace sine of 2x with 2 sine x cosine x. So after I apply the double angle identity for sine of 2x, I replace that with 2 sine x cosine x. My 1/4 gets multiplied into a 1/2, and I have the same factors I had above that I just moved off the screen. The very thing that we were trying to look at. So if you encounter even powers of cosines, you don't want to split things up in parts. You want to change your function from powers of cosine to cosine of multiples of x. Any questions? This seems like a lot of effort for one integral that we could just look up. Knowing the integral of cosine squared is not the point. The answer never is the point in a math class. We like to think that the answer is the point in the math class because the people outside don't care about you learning stuff. They just want you certified so they can justify hiring you. You know what I mean? It makes the position seem more exclusive if they randomly, arbitrarily, for no reason, that's all the numbers, require that you have an MBA, just for reasons. It's not arbitrary, by the way. They just want to make sure the right people get considered for the position. Then all that, because when rules like that were established, if you said this job requires an MBA, even though anybody can do it, just walk off the street, train them, and they'll be fine. If you say in America, in history, only up till about 2022 is it still applying, saying this job requires an MBA greatly reduces the pool of candidates to what you would consider to be the right people. This is why society is fighting you so hard to go to school. If you have a coloration like me, if you have a name like me, then you might be considered the right people, but I wouldn't really be considered the right people. I would be acceptable on the outside, but I don't come from money. I'm only the second generation that's not working class, kill yourself through alcoholism level. I'm the second generation. My dad went to school, and that changed my life forever because it was just assumed that I would go to school. When I got my master's degree, I was super happy, but in the back of my mind, I knew it was a foregone conclusion because of the way I was raised. Does that make sense? And it was not until I started teaching here at Skyline and went to the first graduation that I realized, it's like, oh, wow, it's not a foregone conclusion for everybody just automatically. I had that choice. Full disclosure, I chose to kind of crap all over it for a very long time. I'm 8 years in undergraduate because that's how together my shit was not. I pulled it together in like the last couple of years, but it only serves to remind me, not only did I have to go to school for 8 years because I'm an idiot, I was able to go to school for 8 years at undergraduate, despite the fact that I was an idiot. You know what I mean? And it was not until I came to Skyline, and one of the things that they'll say when you graduate is say, this is the first person in their family to graduate from college. And then the crowd goes wild, as it should. because that is shifting gears for your family forever. And the reason that it's becoming more difficult to do that, of all the things we could talk about, like tuition going up and well, tuition goes up because we have too many administrators. Sorry, administrators, but too many of these. And we put a lot of money into the administration of school, not just the individual people. They do work, and it's important. But the administration is a little bit bloated, and our funding is really lackluster because we don't care about education. Have you noticed the pattern? There are people out there that are actively trying to prevent you from going to school, getting a college degree, and changing the course of future generations in your family. There are people actively trying to stop you from doing that. And the only reason is they don't think you should. So the only reason you really need to pursue this line of work is, well, fuck you. I'm gonna do it despite that. And then when you graduate, make sure you get the attention of all the owners of the country and you give them big middle fingers, because it'll be a big deal. You know what I mean?
Okay. Sorry, I'm not done.
All right. That was a lot for one problem, but it showed us a lot of things that could go wrong and how we could fix them. So that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.